I'm coming to you from the very noisy lands of Canberra, which are the Ngunnawal and the Ngambri traditional lands, and I'd like to pay my respects to the elders of those nations, past, present, and emerging. And
I think, Mitchell, it's hilarious that he barks or she barks it whenever you speak. So we can still hear you fine though. There's no worries in actually hearing you.
I'm going to persist for 30 more seconds and then I'm going to take action, sorry.
Oh no.
Yeah, so I'm coming to you from those traditional lands, and I'd like to pay my respects to the elders of those nations, and I'd like to particularly acknowledge the care for this country that those people have carried on over all that time, and the knowledge of the living things of those countries that First Nations people hold, which relates directly to my talk. Yeah, so this is a little talk that is some sketches for some ideas around seeing living things through machine learning. Resonates weirdly well with a lot of the other stuff that we've seen. As has already been mentioned, a lot of the action around sort of big tech and machine learning has a strangely kind of natural orientation. This is Microsoft's AI for Earth program, which is a big sort of, public good program around AI technologies and environmental challenges. Google sponsors this big program called Wildlife Insights, which is a large-scale kind of cloud platform for doing machine learning analysis of camera traps. What we're seeing here in large part is the sort of image intensification and the sort of data intensification of a lot of environmental science, so conservation, land management, ecology, those kinds of disciplines are now generating huge corpora of images. A lot of those images are generated automatically now or without human intervention through cameras. Oops. And so you end up with a paradigm that's very familiar for the machine learning world. So where we get sort of huge volumes of images of the living world, unstructured data. You tag and classify some of them using sort of expert human judgment. So using experts to sort of tag and identify those images. You train up a model and then you can feed it mountains of images and you get out species and occurrence data. So there's this process of reduction of taking these images of the world and turning them into data that can be ingested into a scientific process much more kind of readily. So in some senses, it is this kind of industrialization of machine learning, and the output, that a lot of the value is on the kind of quality, the ease with which quality data can be generated. I have a kind of critical perspective on that, I guess, and what I want to talk about today is this process in the middle, which is where the model is acting as a kind of a form of automated attention. And so I'm particularly interested in that, like in this process of automating our attention for the living world. And in particular, I'm interested in kind of undoing that. I'm actually interested in how can we kind of prime, engage, facilitate, drive our attention to the living world rather than automating it. Because yeah, a lot of the time in this work, what we're doing is creating an ML that functions so that we don't have to see things. Whereas I'm interested in if instead we might be able to see through ML. So if we might be able to use what ML can do and the images that ML can offer us to actually see again or to see differently. So to kind of look in reverse back through it and to de-automate our attention in some ways, or to divert the automation of attention that machine learning kind of suggests. So yeah, my little proposal is this: how might we see living things through ML in order to actually engage attention and reflection rather than automate them away? And I'm going to talk about 3 little tiny examples, and these are all readings of images that come from the literature in this area. Yeah, a little some prospective thoughts around how we might look at these things. So there are 3 different kind of genres of ML image. They're probably quite familiar to many of you, but in this case, they're all being applied to look at images of living things and biodiversity. The first ones are saliency maps. So saliency map is a pretty widely used visualization that is about identifying which parts of the visual field are kind of relevant. In other words, which ones are particularly strongly associated with a given classification. They've become quite popular in the wave of sort of explainable AI, which is where this Molnar quote comes from. This image comes from a nice little BBC project called A Machine's Guide to Birdwatching. So the image on the left is a magpie, a UK flavoured magpie rather than an Australian one. And the image on the right is a saliency map of that image, where it's a kind of heat map that shows you essentially the most magpie-ish parts of that image. So which parts of that image, which pixels are the most heavily associated with the classification of magpie. And you can see that it indicates that white patch around the kind of shoulder, and as well as the kind of bib, distinctive bib at the front of the bird. So it draws our attention to these particular features of this creature. Here's a couple more that come from a paper I'm going to refer to quite a bit, Miao, Gaynor and Wang, big paper on deep learning and wildlife classification. So the ones on the left, these are from Serengeti camera trap images. So the ones on the left are baboons, ones on the right are impalas. And again, if you look at where the saliency map is highlighting those images, you're getting little kind of glimpses of what is particularly baboony about this baboon image. And you see it highlights the snout and also the kind of curve of the tail, the angle of the tail and the way that it curves. And those beautiful images of the impala, again, it's highlighting particular features. So notice in the top one in particular, there's this strange little spot that's at the kind of around the leg, the haunch of the impala, and it also is really into the patterning of the animal. This paper is really interesting because they go on to do a little study. So they actually compare the saliency maps that ML generates with human experts. So they ask human experts to identify distinguishing parts of the same image. And often there's overlap and sometimes there's not. So in this case, there was largely overlap between the two classifications. This one's particularly interesting because it was actually only the ML that noticed that black spot and identified it as a distinguishing feature. So to me, that's interesting. It suggests that it's possible, even though, and I completely agree with Fabien's analysis just now, that these systems are incredibly conservative and that they can only see what has been seen, that they still might actually know things that are worth knowing and that are interesting, in particular, that might redirect our attention back out into the world. So in this case, yeah, the system has noticed something that human observers didn't about the body of the impala. So what we're getting from these saliency visualizations, you could think of as visual and morphological keys. In other words, they're devices that actually direct and sort of focus our attention. And that's a tradition in the natural sciences that is very, very old. And so we often see these kind of visual resources used in terms of identifying organisms. And there's a huge variety of them. Some of them are kind of spotters guides, so that it's about the organism, its sort of habits and movements. The leaf guide is an example of a thing called a dichotomous key, which is a very formalized structure that basically gives you a set of decisions to make about the thing you're seeing in order to correctly classify it. So these are kind of visual technologies of taxonomy, which are very well established. So I guess what I'm suggesting is that things like saliency maps are, could be almost seen as joining these kinds of visual devices. A couple of examples of feature clustering. We've seen lots of TSNE visualizations already, but essentially the idea here is that with a trained network, you're generating lots of feature vectors, and other than separately to actually the classification of images, you can reveal the shape of the network, its insides, by visualizing the relationships between those features. So again, this is part of sort of cracking open the network and trying to see what it is seeing. This paper, another deep learning classification paper, is also on African animals. And so, I find these images kind of striking in themselves as visualizations of living things, and in particular of the proximity and the affinity between them. So what you're seeing are the different species that are classified and the way that the TSNE visualization lays them out into their separate kind of islands. But you also see that there's these patches of kind of continuity. So in particular, I'm interested in this kind of like, bit that joins buffaloes with wildebeest, and also links up with warthogs over on the right there. There's this kind of speckled continuity, which to me is very interesting, suggests maybe these things are not so distinct after all. Maybe they are sort of somehow continuous, contrary to, the traditions of kind of Linnaean taxonomy. And if you have a look at the creatures, if you wouldn't know a wildebeest from a buffalo, I'll show you some images of them. So there's a wildebeest, there's a buffalo, and so they are actually extremely similar. They've got really similar shaped horns, and they're big shaggy things with ears. So you could see how a network would align them side by side. And there's a warthog. Again, some similarities, particularly in terms of the horn tusk kind of parallels. So the network is actually showing us features of these living things and their affinities as well as their distinctions. Here's another feature map. This one's bumblebees. So these are all bumblebee species. Who knew there were so many bumblebee species was my first response. But again, it's showing us these strange and interesting affinities and relationships. And so here there's this merger between Bombus flavifrons and Bombus sitkensis. And yes, they are extremely similar. They're both fluffy and they both have that yellow section around the middle. Here are two others that are also really close. These are both bumblebees from the arid kind of areas of the Western USA. So again, similar thing with the distinctions are sort of what this image does for me is creates a kind of visual space of living things that organizes them in a way that is novel and that can actually, again, attune us to the relationships between them, to their kind of qualities. Here's another one that's from that Meow paper. Again, this is a different device. It's not a T-SNE, it's a sort of visual taxonomic tree that's hilarious because it just jams things together in this strange visual way. So there's this group that consists of porcupine, warthog, buffalo, wildebeest, etc., which they describe as the relatively large body to appendages group in the paper. There's also a small to medium-sized antelope cluster and an animals with prominent tail or big ears cluster. So they're making these kind of strange ad hoc morphological groupings based on what the network is spitting out. So third quick example, activation patches. These are little visualizations that show parts of specific images, so input images, images from the corpus that maximally activate particular neurons that are linked to a specific class. So in other words, this image here is showing us the 5 neurons that are most linked to the class genet, and each grid of 9 is the 9 image patches that most activate this neuron. So you're getting the sort of flavor of 5 neurons and the kind of things that those neurons really fire for. So in this case, like the top one really likes the sort of stripy tail. The second one is more about the sort of the body, etc., etc. There's some interesting artifacts that emerge through these. So this is reedbuck. Now have a look at, in particular, numbers 3 and 4, to just mostly fields of grass. But yeah, they're among the most highly activating neurons for that class. The authors explain this essentially as kind of an error. They say, note some of our patterns are primarily backgrounds. And that the network learns to associate certain backgrounds with species. They account for this as kind of a data problem. They say, oh, this is because particular cameras have common backgrounds, and so therefore all we need essentially is more data. So it's the usual kind of disclaimer that, oh yeah, this problem would go away if we just had a bigger corpus with enough different backgrounds, which I think is interesting. But for me, I would like to kind of read against that. This wildebeest one is fantastic. What is a wildebeest? A wildebeest is apparently mostly just this kind of muddy field, which I think is fantastic. So what's going on here is this relationship between figure and ground, and which is also a relationship between the animal and the environment. And one of the things I think we can learn from machine learning in this case is a refusal to acknowledge that distinction, or a willingness to blur it, or a happiness to kind of surf between it. This distinction, this binary of animal environment is so canonical, but also it's been contested for so long. This is Gibson saying animal environment are inseparable. Each term implies the other. you know, every animal has an environment, every environment has an animal. So how can we imagine these things as anything other than separate? And yet, of course, science is still very founded on the separability of these things. Machine learning actually might be able to help us see that they're inseparable, I think. There's, of course, this tradition of, you know, of in biology and museology, and of course, colonial extractive cultures, of separating the figure from the ground, you know, and that tradition still exists. But equally, there are other formations which are not figure ground, which, if anything, are just lots and lots of figures all the way down. You know, this is a food web that comes from scientific work on the mouth of the Murray River. So in ecology, you know, there is no figure and no ground. It's you know, it's a network of figures. And this reminds me of this kind of famous kind of blooper from one of Google's papers, Inceptionism, where they note it, where they're talking about ImageNet, and they discover that, you know, there is no dumbbell without an arm. And again, they call this a mishap. Our visualization can help us correct these kind of mishaps. Again, I think that's actually really interesting. Of course, there's no dumbbell without an arm. There's a relationship there that's actually being revealed. And so, yeah, I would say, is this a bug or is this a feature? I'd like to think of it as more of a feature. I'm going to finish in a sec. So I guess, how might we see living things through ML? I've talked about these three things and tried to pull out a few of their possibilities. So saliency maps give us this kind of a new direction of attention and direct our attention in quite close ways that we can kind of apply as human viewers rather than machine viewers. Feature clusters show us these kind of weird new morphological spaces. They let us organize living things in strange new ways and notice differences and similarities. And these patches allow us to question this distinction of organism and environment, and also just, you know, reveal more about these relations, the inescapable relations between living things and the worlds that they inhabit. That's all from me.